Hi, my name is Amy Haley. I teach pre-AP and AP biology in the Madison City System at James Clemens High School. I'm going to be going through the data analysis PowerPoint that is being used as a part of the workshop that you are attending this Friday at Auburn University. So this is a PowerPoint presentation that has been modified from one that I actually complete with my students in class. I do this on about the second or third day of school. I really like to start my kids out on the right foot when it comes to the true nature of science, which is collecting data and analyzing those data so that we can actually draw conclusions from it. Data analysis is used to characterize and determine the strength of patterns within a researcher's data. This is a very important and emerging field that our students really need to have a grasp on. They really need to understand just some bare bones basics of the data analysis process and some of the statistics that are involved in data analysis, because there's going to be so much information thrown at them over the course of their lives. They just really need to have a background in the ways that these data points can actually be interpreted and understood. So we're going to spend a little bit of time talking about data analysis and particularly focusing on a statistical tool that is very widely used by biologists and other scientists. Now, we're using data sets that were collected from Dr. Hood's lab at Auburn University. Dr. Hood studies reproduction in mice, and she generally separates out her mice into two separate groups, one of them being the experimental group that are allowed to reproduce, and one of them being the control group, which are not. What we've done here is give you information about the samples of each one of these particular groups. So we've picked out 6 mice from the experimental group and 6 mice from the control group, and have presented you with data about the mitochondrial respiration rate that's occurring in those mice. We're going to be using these data sets as we go through and practice this data analysis. Inferential statistics is what we're going to be focusing on. It involves inferring values in a natural population from a sample. Dr. Hood and her students use these inferential statistics to characterize patterns that are common to mice, but other scientists use them for many other things. Really, any kind of statistical tool in science is going to be largely inferential because we don't have the means or the capability really to sample an entire population. We take small subsets, sample sizes of that larger complete population, and then draw conclusions based off of what our sample size and our sample group tell us. It's just a more practical way to go about doing science because, for example, surveying every human on the planet to find out what their favorite color is really not cost efficient, and is really not the best way to go about doing that when you can just sample 100 of them and generalize from there. So we're going to be focusing on this idea of sample sizes being used to represent or draw conclusions about the whole. What you see before you are two separate populations. One is a population of 6-month-old mice that have only reproduced once, and the other is a population of 6-month-old mice that have never reproduced in their lives. So we're going to pull a sample from each of these different populations. We're going to have 6 mice from the reproducing group. We're going to have 6 mice from the control group. So the sample size for each of our groups was 6 from one and 6 from the other. And again, we didn't use every single mouse because it's just not, while it would give us a complete data set, it's not effective as far as cost, as far as time. It would be wonderful and awesome if we could. It's just not one of those things that scientists really have the time and just the ability to be able to do. Now, most of the data that we're going to collect are going to fit into 2 categories. They're either going to be measurements or they're going to be counts. Our data are 99% measurements, meaning that they've got a unit associated with them. Centimeters, liters, inches, miles, all of those are units that we use to describe data points, and those are measurement data if they've got a unit that's associated with them. Count data are just tallies. It's a frequency that you're generating of a particular category. Count data is wonderful, and we actually do use it quite frequently in science. However, we, for our statistical purposes, are going to be focusing on measurement data, on those data points that do have different types of units associated with them. Most of the measurements that we are going to be looking at, and most of the time you can just pretty much assume that measurements are going to be continuous. That means that there's an infinite number of potential measurements over a given range. What you see on the screen are what we lovingly call in science bell curves. A bell curve is a graphical representation of this idea that measurements are continuous, that they exist on a continuum over a certain amount of ranges, and that there's an infinite number of potential measurements that you can get over the course of that range. Now, generally, this is where I pause in the PowerPoint presentation and I start to emphasize the importance of graphing data, representing information with pictures and figures. I ask my kids, okay, so here's a graph. There are bell curves on this graph. What can you tell me about the experiment that these people have completed? What can you tell me about their methods? What can you tell me about the conclusions they might have drawn just by using the information on the graph? So we talk about the axes, what the axes represent for us. We talk about how once the curve is plotted with the data points, we can actually draw some conclusions about what these people were doing. They were obviously looking at height. They were obviously looking at male height versus female height. And they were really looking to see where male and female height overlap, where you have women displaying male height and then men displaying female height, or traditionally what we would consider those categories. So it really lets the kids kind of shift from, oh, okay, I know how to do science, I know how to generate means, I know how to do all this other kind of stuff, to start thinking about it in a graphical way, because that's really what we're going to be heading towards with our statistical analyses. Count data, as I said, are not measurements. They don't have a unit associated with them. They are discrete data points like the number of leaves on a stomata or the number of white-eyed individuals. Those are tallies that you can, put down on a piece of paper and then count how many you have at the end. And there's not really a unit associated with that. While very valuable information and very useful in the realm of science, it's really not going to be the focus for our statistical analyses. We're really going to be using those measurement data points, those points that have a unit associated with them. So, quantifying respiration in mitochondria represent measurement data, not count data, and this is what Dr. Hood and her students are doing in their lab. They're actually measuring how much oxygen the mitochondria use. They're generating measurement data points, and they're then going to be running these inferential statistics to accomplish data analysis of the information that they are collecting, so they can draw some conclusions about the overall population using the sample size, or using the sample that they have selected from that. Now, descriptive statistics summarize the data. Basically, they're used to describe patterns and variation in the data points. They allow us to talk about the numbers in very pattern-like ways, where we can actually see and pull information from just the general numbers themselves. What you see on the screen is just a data set. That means absolutely nothing to anyone unless you are the owner of that data set and you know what all those numbers represent. Numbers for the sake of numbers are not worth anything. We really have to crunch those numbers and figure out what they mean, get at the root of the patterns that are involved in that process, and that's where these descriptive statistics come in. Dr. Hood uses these descriptive statistics to determine the average mitochondrial respiration rate for each of the groups that she has generated. So again, this is the same information that we had at the beginning of the presentation. We've got a control group, we've got an experimental group. The control group are the mice that were not allowed to reproduce. The experimental group were the mice that reproduced one time. Still have 6 from our control group and 6 in our experimental group as our sample size for each one of those categories. So, just diving right in, let's do some descriptive statistics. How do you calculate the average? Generally, this is where your kids are going to say, oh, I know, you add everything up and then you divide by how many you have. And that's correct. That is the way that you calculate average. But there's a lot of different ways to look at the idea of an average. And if your students start to think of the average in a different way, that's going to help them as they're starting to dig deeper in this data analysis process, because really, average is no longer enough for us. Maybe when they were in 7th grade, average was good. That's all their teachers wanted them to be able to generate, but we are going to ask them to go much further than that. So let's start looking at what it really means to calculate the average. Obviously, you can add them all up and then you can divide by the number that you have as the sample size. So we've got 6 as our sample size here. If we add all of those respiration rates together, we're going to get 216.6. Divide it by the total number, and you get 36.1. That's the easy way. That's the way they learned how to do it way back when they learned how to do statistics the very first time. You can also talk about the average as a mean, which is the real term that most mathematicians use. They don't really say average, they say mean. And they use X bar to represent the mean as a symbol. That general overall process of the mean representing the sum of individual data points divided by the sample size is represented in the equation that you guys see here. It's summarizing the entire sample for us, and it might provide an estimate of the entire population's true mean. This is why average is no longer enough, because sometimes the average, if your data set is not a good data set, is not going to give you a really good idea of what that population is really like. You have to test the average. You have to put that average to a measuring bar to really see if it's giving you a true representation. So, using the same symbols, X bar meaning mean or average, sigma meaning sum, the X representing an individual data point, and the N representing our sample size, we can actually change the way that you think about the idea of an average. So this is the same exact equation as you just saw. It's just been a little bit more mathed, if you want to think of it like that. You've got X bar, which is our mean. That is going to be equal to 1 over the sample size multiplied by the entire sum of each individual data point, that's the xi, multiplied by that 1 over n. I apologize. So you're doing the same thing mathematically. It's just multiple ways of looking at the same process. And this is kind of the way we want our kids to start thinking, because this is very much how science is. There's multiple ways of looking at the same problem and approaching the same problem. You may not all look at it and view it in the same manner, but you're probably going to get to the root the same way. And that's kind of what we're showing here with these different equations. Now, let's talk about the average itself, the mean. Alone, that particular data point or that particular set of analysis information is not worthless. It's actually a good thing for us to know what the average is. But if you don't have a way to test the average, you're not going to know if that average is a true average or if it's just an average of really bad data that you collected over the course of your experiment. So that's where we bring in these ideas of variance and standard deviation, represented by S squared and S respectively. They measure how far a data set is spread out. So if you look at the representation that is on this slide, you're going to see that the average of this particular data set is 36.1. That average is what we calculated from the tables that we looked at before. You figure that out the same way you've always generated averages, the way you've always generated means. The other data points are the individual discrete points of information that we collected over the course of our experiment. And what we're learning using variance and standard deviation is how far, on average, each of those data points is from the mean. So we want to see how wide, how spread out our data are using variance and standard deviation. Now, obviously in science, you don't want really large spread out data. You want your data to be very concise. We want small variance and small standard deviation, because that tells us that all of our data points are living right there really close together, right around that average in the middle, which shows us that we have a really tight pattern forming. And that's good. That's what we want. Really large variance, really large standard deviation means your data are super far spread apart and probably not as reliable as you would really want them to be. So this is allowing us as researchers to see just what that average is telling us. Is this an average of data that are 250 points away from each other, or is this an average of data that are only a few points away from that middle average bar? That's what we're looking at with these two different values. Just for point of reference, a variance of 0 means that all of the values in the data set are identical. So if every single data point that you collected was 38.8, then they would not be anywhere far away from that particular average. They would all be the average, so you would have a variance of 0. There's no spread there. They're all on that same middle line. Okay, so let's look at how to calculate these. The equations for variance and standard deviation are given to you guys below. Pretty much, we would tend to rely more on standard deviation than on variance because variance is in the wrong units. Variance is S squared, which means if you were collecting data in millimeters, then variance is going to give you a particular value that is millimeters squared. And that's not what you were collecting your data in. Your data set is not millimeters squared, it's millimeters. Standard deviation is nothing more than just the square root of the variance. And all it does is this really cool Jedi math mind trick that allows you to put your units back into the correct form that your original data set had them in. So variance and standard deviation are essentially the same thing. You're looking at the same information, but we tend to talk about standard deviation because it's in the same units as the data that we collected. Please don't let the equation scare you. Most of the time, especially I know my kids, whenever they see a radical bar, they freak out because they're going to have to do square root. They all have a calculator. No one's asking them to crank out this stuff by hand. No one's asking them to do it in their brain without scratch paper or anything like that. So please don't let them freak because they're seeing a radical bar. They can do this. All of those symbols they've seen before. Sigma is sum. The X is an individual data point. X bar is the average or the mean, which we all know how to calculate. N is the sample size. So all of the data values they should be able to find from their information, and it's just a matter of putting it into the equation. So let's work through an example, okay? Now, we took one of Dr. Hood's data sets, one sample from a particular population. We took 6 mice, so our sample size, our N is 6. We have generated a respiration rate for each of those mice, and we've already calculated a mean. You did that before. We looked at how to figure out the average of that data set. It's 36.1. Now we're going to put that average to the test. We're going to see if that average is really doing a good job of representing this particular population, or if those data points are really spread out and we have a really large standard deviation and just data everywhere where it's much more unreliable. Now, we've highlighted for you where that mean is going to exist in this equation. It's your X bar, and it's never going to change. It's going to be the same for every step of this process for this particular population, 36.1. Now, once you've calculated the mean, the second thing you do is you go in and subtract the mean from each individual data point that you have collected. So all we did was add a column to the table that you guys see on the screen. The mitochondrial respiration rate was 42 for our first mouse. We're going to take 42 and subtract the average from 42. That's going to give us 5.9. Now notice, as we go through and do that for each individual data point, 42 minus the average, 31.4 minus the average, 38.8 minus the average, we're going to generate some negative numbers. Please don't panic, and please don't let your kids panic. Those negative numbers are about to go away, because if you look back at the equation, the next step of the process is to square each of those values that you have just created. So we're going to take 5.9, we're going to hit the square button all the way down that column, and that's going to give us this fourth column that we've generated for you guys here on the screen. So 5.9 times 5.9 is 34.8, so forth and so on. Now, again, using that equation as our reference point, the next step of the process is to take all of the information that we have just generated in that fourth column and add it all up. So we take 34.8, 22.1, 7.3, 60.8, 72.3, and 21.2, and that gives us 218.4. The rest of our equation up at the top shows that we should divide that sum of each individual data point minus the mean or average squared by the sample size minus 1. Our sample size was 6. We've got 6 separate mice represented here. We're going to subtract it by 1. That gives us 5. So we're going to take 218.4 and we're going to divide that by 5. It's going to give us 43.7. Then you've got that radical bar. You just hit your square root button, and that tells us that the standard deviation of this particular data set is 6.6, which is actually a really good standard deviation. That means on average, each of our individual data are 6.6 units from the average of the sample.
Okay, so on average, they're 6.6 little steps apart from each other, which is good. That means that they're relatively close together, because you can have standard deviations all the way up into the hundreds, and we don't want that. We want them to be nice and concise, like 6.6. So once we do those statistical processes, you can complete it for the other data set as well, which was our experimental group. We've got the same set of information. We went ahead and did that for you just for sake of brevity. The average for that experimental group was 63.5. If you run the statistics, you're going to get a standard deviation of 8.7. So our experimental group has a little bit of a larger spread on the data. The data are a little further apart than our control group, but still 8.7 is a very good standard deviation value. Now, what do we do with that? Now that you've run all these numbers and you've gotten your kids all excited about math and all the stats that they're doing, and they feel really accomplished and very sciencey, what do they do next? Well, they take the two values that you've just generated, the averages and those standard deviation amounts, and they put them on a graph. They present the data in a way that other scientists can interpret it. Now, our two common types of graphs are going to be bar graphs and scatter plots. We're going to focus on a bar graph for this particular experiment because it really, using standard deviation is, in my opinion, one of the best ways for kids to represent their data. And they feel really comfortable with bar graphs. They can all make bar graphs. They feel good about them. It gives them a little bit of comfort in this, giant little labyrinth of statistics that we've thrown them into with this particular activity. So let's take a look at how to create this graph using those values that we generated from our stats. We're going to have our X and a Y axis just like we normally have. We've got our two groups set up here for our control and our experimental groups. We are graphing with the bar the average of the control group and the average of the experimental group. What you see sticking up from and below each of those bars is an error bar. The error bars we generate based off of the standard deviation. So if we go back, let me scooch back to this. This was our data set. We have averages of 36.1 and 63.5. So that's what we're going to make our bar on our bar graph for. Then we have standard deviation of 6.6 for our control group and 8.7 for our experimental group. So if we go back to the graph, we're going to add 6.6 and subtract 6.6 from the average of our control group, of that green bar that we have on our graph. And that's where you have this little tiny error bar above and below that average bar that you've created. We do the same thing for the experimental group. You're going to add 8.7 to the average and subtract 8.7 from the average, and that's going to generate that error bar that you can see and superimpose onto the average bar for that particular graph. Now, I know that's a lot. It's a lot of math just to get you to creating a bar graph. But really the bar graph is the goal, because what we're doing in this experiment is we're comparing control group with experimental group. We're comparing these mice that were not allowed to reproduce with mice that only went through one reproductive event. And what we want to know is, are they different? Are they statistically going to be different from one another? Based on the standard deviation, based on our data analysis process that we have completed, and based on the graph that we have generated from that statistical analysis process, we can say that yes, they are likely to be statistically different because those error bars do not overlap one another. If the error bars overlapped in any way, then we could not say with confidence that our control and our experimental group were statistically significantly different from one another. They would essentially be the same, and we would not have found anything of meaning. Really what we're getting at with these statistics and this data analysis process is we want our kids to look at an average and say, okay, what does that average mean? Is that average reliable? Is that average different enough from the average of another population to actually show a significant difference between these two separate things that I'm looking at? We want them to start to think deeper, to really, really start
analyzing the data that they collect and not just settling for an average, which at this point really is just, it's not good enough anymore. They need to be pushing the envelope, and we know that they can. I really feel like equipping my students with these skills has helped them be more confident in the data that they collect over the course of a lab in my classroom. They want to run the statistics, which I find very, very, very exciting as a teacher. They want to see if their averages are good. They want to see if they've actually found something statistically that they can then report back to me as a result. So I really hope that this video has been helpful for you guys. I appreciate you spending the time and investing in your students and just wanting them to be better. That's our goal as teachers and as educators. We want our kids to be better. We want them to want to know more. And I just applaud you for taking the time to really invest in yourself so that you can turn around and allow your students to reap those benefits. I hope you guys are having a great day, and just let us know if there's any way that we can help you out. Thank you.